Hello and welcome to this lecture. We're going to continue what we studied in the previous lecture where we defined adjoint of a linear map. So in this lecture we're going to start looking at properties of adjoint, and this adjoint will play quite an important role in all that we're going to study later in the remainder of this course, classifying operators, etc. But right now we're still looking at linear maps, the more general linear maps, and what does it mean to work with adjoint, what kind of properties it satisfies, and all that. Okay, so let's get started. Quick recap. I think the first part I'll quickly go through, and we're really looking at adjoint right now. We are in inner product spaces. We're considering orthogonality, orthonormal basis, and that has resulted in quite a few simplifications. In particular, the definition for adjoint of a linear map has this very nice characterization in terms of what it does with inner product, right? So you have a vector v, which is taken to TV by a linear map T, and then if you have a W, which is another vector in W in the range of not in the range of T, but in the other second subspace into second vector space into which you're going, that one. And if you look at the inner product of TV and W, it turns out there's always a T star, this one adjoint operator, which can take W to the original vector space V, and on that the inner product is sort of preserved. The V with T star W inner product is the same as the TV inner product with W itself. Okay, so that picture that you have with the adjoint is very interesting, and this gives a lot of nice properties for the adjoint. Okay, so let's see what those properties are. So to clearly explain these properties, we'll look at three different finite inner product spaces. They're all over the same field, R or C, and the first property is quite easy to see why this should be true. We'll prove all of this, at least one or two. I'll show you the proof. The method is very similar in proof, but these are all sort of intuitive given the linearity of the whole thing. All this should work out, right? So if you look at the sum of two operators, S and T are two operators from V to W, and you look at the operator, I should say linear map. Okay, so let me not say operator. S and T are two linear maps from V to W, and you look at the linear map S plus T. Okay, and then you ask what will be its adjoint. Okay, and it turns out that is equal to the adjoint of S plus the adjoint of T. Okay, so this is linearity for the adjoint, like additivity for the adjoint. The second one shows a slightly different property with respect to homogeneity. If you take a linear map T and you scale it by lambda and you look for the adjoint, it turns out it is lambda bar. There is that conjugate, pay attention to that, this conjugate here. It's a small little bar on top of lambda, but that makes a difference. So lambda bar times the adjoint of T, okay, for any lambda. So of course if you are in a real space, then this lambda bar will become lambda, there's no problem there. But if you are in a complex vector space, then this lambda bar will matter. Okay, and then if you take the adjoint of T and ask what is its adjoint, okay, so you can do, I mean, adjoint of T is after all a linear map from W to V. Of course, you can ask for the adjoint of that operator. It turns out you go back to the original operator T. Okay, original. I keep saying operator, but this original linear map. Okay, so we're in the more general world of in a linear map which goes from V to W, and not necessarily operator which goes from V to V. Okay, identity operator. Now we are an operator. It's an operator. It goes from V to V or W to W or anything. The adjoint of the identity is identity itself. These are all easy to see. You know, identity does nothing, so the inner product should also do nothing. Okay, inner product will be preserved just by itself. And here's an interesting property. If you have two operators S and T which you can compose, okay, you can compose in this fashion S and T. So notice what's going on. T takes you from V to W, and S will take you from W to U. So ST is well defined. Okay, so you can look at ST, which will be an operator from V to U, isn't it? I keep saying operator, but it's a linear map. Okay, so ST is a linear map from V to U. Okay, now you can ask definitely the question of what is the adjoint of ST. It turns out that's equal to another composition here, but in the reverse direction. Okay, you can do adjoint of T and then S of T. So as in S adjoint composed with T adjoint. Okay, so this is a relationship. The order reverses, but the adjoint works. And you can see this composition is well defined, right? S star, S adjoint is from U to W. Okay, and T adjoint is from W to V. So T adjoint times S adjoint is actually from U to V, okay. ST is from V to U, and T adjoint S adjoint is from U to V, and that's correct, okay. That's the correct way in which the adjoint will work. All of that works out, okay. So I'm not going to prove all of these. I'll prove maybe, I think I've written down proof for 1 and 2. I'll just quickly walk you through. The philosophy is always the same. The proof for this adjoint property always uses that inner product relationship, right. So I have this S plus T whole adjoint. What property do I know it satisfies? An inner product with V with the adjoint of S plus T W is always going to be equal to the inner product of S plus T V and W, right. So this is the starting point, okay. Then once you come to this world where there is no adjoint, you use all the properties you have, or even if there is adjoint split out, you use all the properties of the inner product, right. S plus T into V is SV plus TV. So since inner product is additive in the first argument, you will get SV comma W plus TV comma W, and then you use the adjoint property on each of these things, right, individually. Now that you have come to individual, you can use the adjoint property there. So this first SV comma W is V comma S star W, TV comma W is V comma T star W. Now you use the additivity in the second argument, and you will get V comma S star plus T star W. So if you look at the first and the last now, okay, you compare the first and the last, you have your equality, okay. So S plus T whole adjoint is S adjoint plus T adjoint. Is that okay? So you have that whole relationship, okay. So just go through this proof and convince yourself that every step was valid, have not made any mistake, and check for yourself that this whole thing is true. So now once you have a relationship like this, this S plus T adjoint operator should be equal to S adjoint plus T adjoint, right. So think about why that is true also. You can sort of prove that to be true. You can bring it to this side and show that that operator has to be 0, okay. So it's not too bad. It's true for all V, so this has to be true, okay. Okay, so now look at the next one. The second is the proof for the claim 2 here, and here again we are looking at lambda T whole adjoint W, whole adjoint. So we start with this inner product V comma lambda T whole adjoint W, and then we use the property here. So this is going to be equal to the inner product lambda T V comma W, and you can pull the lambda out and you get T V comma W, and T V comma W is V comma T adjoint W, and then you take lambda into the second argument. When you take it into the second argument, you have to do lambda bar, right. So that's how we define the inner product. So you get lambda bar T adjoint W, okay. So this now again you can compare these two guys, and you quickly identify that lambda T whole adjoint is equal to lambda bar T adjoint, okay. So that's the proof. The other three I will leave it as an exercise. You have to write very similar proofs. Everything will work out in the exact same way, and you will be able to identify what happens when you do adjoint of a some modified linear map. How does it relate to the adjoint of the original linear maps, okay. So you can do all this. So these are good properties to keep in mind. So this additivity, homogeneity, sort of conjugate homogeneity properties, and the repeated adjoint, what happens, all of this is easy to, you should remember this because it will come handy quite often. Okay, so more properties. So adjoint we know is a linear map, right. It's if T is a map from V to W, T adjoint is a linear map from W to V. So of course it has the null space, range space, all these other routine properties that we have for a linear map, okay. And it turns out those spaces are related to the similar spaces for the original operator T, okay, and those relationships are captured here, okay. So this orthogonal complement will enter the picture, and you can see it plays a big role here. Look at the first result, for instance. It says, so it's good when you look at a result like this to also think of what vector space each of these things are a subspace of, and I mean just think about that because sometimes it can be a bit confusing, so you should be clear on that. So null T star is actually a subspace of W, right. So range T is also a subspace of W. So null T star, null of the adjoint of T, which is a subspace of W, is equal to, apparently, we will prove this, but this is a property here, it's equal to the orthogonal complement of range of T. So clearly this is also a subspace of W. So it's quite believable that this might be true, and one can see we will prove that this is exactly true. So the null of adjoint is equal to the orthogonal complement of the range. Okay, so these are all these. So this adjoint and the original operator are tied together in a very strong way through this inner product, and so it's sort of believable that these things happen. Okay, and there is a very precise relationship here, right? So null, remember, null is something that makes the subspace which is orthogonal to the to T in some way, right? So it's not difficult to imagine that this this kind of property ends up being true. Okay, so we'll see how this works out. We'll prove this. You'll see it, and similar properties are true. So in fact, I mean, once you see 1 is true, 1 and 3 are related, right? What is 3? How do you get 3 from 1? Simply put T equals T star. Okay, if you put T equals T star in 1, you will get 3. Okay, isn't it? So 3 is not a new result. 3 is simply a corollary to 1. Okay, and in fact, even 2 or maybe 4, even 2 is sort of related to maybe not 2, but so all these guys are related. So you can do 1 and 4. If you look at 1 and 4, these are also the same thing, right? See, if you take complement on both sides, if you put T equals T star, from 1 you get 3, and if you take if you put complement on both sides, if you take complement on both sides, you simply get range T equals null T star complement, right? So you have taken complement on both sides, range T complement will become range T itself, and you will get null T star complement. So 4 is actually simply a restatement of 1. Remember, 3 was a restatement of 1, 4 is also a restatement of 1. Now once you have 4, you simply put T equals T star, you will get 2. Okay, so right, if you put T equals T star in 4, you get 2. So this 1, 2, 3, 4, even though they all look very different, it's just only one relationship. It's enough if you remember one of them, whatever one you prefer, your favorite one. You remember one of them, everything else is obtained by either complementing or putting T equals T star. Okay, so as long as you remember that, this is okay. Alright. And here is this other nice relationship. The range of T and range of T star have the same dimension. Okay, so this is another thing that we will see. This is actually, if you take one of these results and use fundamental theorem, I think 2, you can take 2 for instance, and use fundamental theorem along with the dimension of the this property, you will get the answer. So it's not very hard to prove this result, but it's good to take any one of these results, you will get it. So it's just a question of using this, but maybe slightly a non-obvious property that range of T and range of T star have the same dimension. We will relate it to something else also later on, but this is interesting to see. So these are nice connections between null space, range space, and various dimensions for T and T star. Okay, so notice this. So range of T and range of T star have the same dimension. Okay, so it's an interesting relationship. So let's do a quick proof for these things. I will prove the first one. Okay, the first one is what's being proved here. Okay. Proof is for the first result, and all the others will quickly follow. You'll see it's quite easy to see. Okay, so to show this, I'll start with a vector which is in null of T star. Okay, T star is remember, it's the adjoint. It's a linear map from W to V, and null of T star. W is a vector in null of this linear map, which means what? That's true if and only if. I keep doing the sequence of if and only ifs. T star W is 0, right? Right, that's sort of the definition. So this T star W is 0, you can also write in an inner product form. So this inner product form is very important. This is true if and only if V comma T star W is 0 for all V in V. Okay, it's not too difficult to imagine. So you take a W, T star W itself becomes 0. So clearly V comma T star W will be equal to 0 for all V in V. Right, so this is okay. Now once you have this, look at what happens when you use the property of the adjoint. Here is where the property of the adjoint comes in. It's a crucial step, right? Up to this, it's all trivial. V comma T star W is 0. Yeah, I mean, of course, If this is 0, it has to work out. If it is 0 for all v, then T star w also has to be 0, right? So we know how the inner product works. That's how it is. So this switch is what's critical. Notice what happens. V comma T star w by the property of adjoint becomes TV comma w. Okay. So this w belongs to null space of T star if and only if w inner product with any vector in the range of T, Tv, right? Tv for all v in V is what? Any vector in the range of T, right? This has to be 0, all right. So this is where the crucial thing comes in, and if this has to be 0, then clearly, w belongs to the orthogonal complement of range of T, right. So every vector in the range of T is orthogonal to w if w belongs to null T star, and it's all if and only if. You can go the other way also, okay. So w belongs to T star if and only if w belongs to complement of range of T, and notice how this nice relationship came about because of this property of the adjoint. Okay, so this is important to note. Okay, so clean little proof, but go and think about what it is. Maybe draw a couple of pictures if you like to understand where this came from. But this is true. So null of T star is range of T complement. Okay. So the other proofs can quite easily be done. I think I illustrated the next part. How do you get, once you get 1, how do you get 4 from 1, which is just the complement. 3 is setting T as T star, and 2 is the complement of 3, I say. Yeah, so 2 is the complement of 3. You can also see 2 as the setting T equals T star in 4. Okay, both of them are possible. So the others are easy to prove once you prove 1. Okay. For 5, I have said use fundamental theorem of linear maps on 3. Yeah, you can use it on 3 if you like. You can use it on 2 if you like. You can use it on one of these 2 and you will get it. So let me maybe show you how that is happening here. So I've said 3. So if you use this, so this tells you null of T. Null T is a subspace of V, right? So dimension of V minus dimension of range of T, right? So that is dimension of null of T, that equals range T star. So range T star, remember T star is from W to V, so range T star is a subset of V. So the dual of range T star will have again dimension, which is this. Okay. So you can cancel dimension of V and you will get dimension of range T equals dimension of range T star. Okay. So looking at this relationship, you may be tempted to think that dimension of null T is also equal to dimension of null T star. That need not be true. You can see that none of these results will give you that. It won't work out because dimension of V and dimension of W can be different. Okay, that is the problem. If dimension of V were equal to dimension of W, then you can say other things as well. But in general, that need not be true. But whatever be the case, range of T and range of T star will have the same dimension. Okay, so that's a proof that we have done. Okay, so this is good properties. So if you notice the previous slide, we saw properties on manipulating linear maps and what happens to the adjoint, and now null spaces, range spaces. There's some powerful results for adjoint and T. So adjoint and T are sort of strongly connected. They are very similar to each other in some fundamental ways. Okay. So now what is the connection between matrix representation of linear maps and adjoint? Okay, what is the matrix of the adjoint? How is it connected to matrix of the original linear map? Okay, so this might be a question that's of great importance, and it turns out there is a very simple and nice answer. If you have matrix representation with orthonormal basis for both V and W, the adjoint of a linear map T is the matrix representation is simply given by conjugate transpose. Okay, so it's a very simple answer, and it also has a bearing on many of the previous results we discussed. So it's nice to look at. Okay, so I've captured that here, but the orthonormal basis is very important. Usually we use standard basis, so it's always true. But if you're not using an orthonormal basis, then this result of conjugate transpose is not true. Okay, so remember that. Okay, so let's see how that is developed. So once again, we have two finite dimensional inner product spaces and an operator T, a linear map T from V to W, and we have two orthonormal bases, one for V and one for W. Okay, I've used N and M as the dimension. Okay, the matrix of T with respect to BV and BW is we will denote it as MT comma BV comma BW, just to say V has basis BV, W has basis BW, and then the matrix M represents this operator T with respect to those two bases. Okay. So, here is the big result. The matrix for the adjoint of T from with BW as the basis of V. Remember, T star will go from W to V, okay, with BW as a basis for W and BV as a basis for V. So, notice the reverse thing there, that will also happen. That is simply equal to the conjugate transpose of the original matrix we had for T itself. So, what is conjugate transpose of a matrix? You transpose it, make every row column, do the row column interchange, and you conjugate each element, do a complex conjugate of each element. Of course, if your field is reals, then the conjugation will have no impact, only the transpose matters, and but if the field is complex, the conjugation will have a change in the entries. Okay, so this is something to keep in mind. Okay, so proof is not too complex. I've written it down here. I'll quickly walk you through it and I'll let you think about it. It's quite an easy proof. If you look at the ijth entry of the matrix MT BV BW, okay, what do I do? So notice what is M T BV BW. So if you look at the column, you have TE1, TEJ, let's say, right, TEN. Okay. So each column, the jth column is TEJ coordinates in what basis? In BW, right. So you find TEJ and find its coordinates in the basis BW and write it as the jth column. So what will be the ith entry? Remember, ith row, if the ith row were here, what will be the ith entry here? It's the coordinate of TEJ for Fi, isn't it? Now Fi is, this F is an orthonormal basis. So what is that coordinate? Inner product TEJ comma Fi. Okay. So you can see that just neatly works out as TEJ comma Fi. So notice how this orthonormality is very, very crucial. Otherwise you won't get this inner product formula for the entry there. Okay. So this is important. So now you use all that you know about adjoint. Okay. So TEJ comma Fi is the same as inner product EJ comma T star Fi, right? And then you do the conjugation, it's T star Fi comma EJ whole conjugate. Okay. All right. Now what about the jith entry of M of T star BW BV? It's the same thing. Okay. So this thing is the exact same thing, right? See, T star BW BV will be T star Fi. I'm looking at jith entry, right? So T star Fi inner product with EJ. And so you see the Ij becomes Ji, this entry becomes its conjugate. So that's where you get the conjugate transpose from. Okay. So simple proof, but nevertheless it's a good idea. Good thing to go through this proof once again. You'll understand the mechanics of it a little bit better. Okay. So transpose, conjugate transpose and this adjoint operation are very, very closely and intimately connected. And if you go back and interpret the previous result we had on null and range space in terms of the 4 fundamental subspaces of the matrix, this notion of transpose will become very clear to you. Connection between transpose and adjoint will become clear to you. So let's do that. Let's look at adjoint and 4 fundamental subspaces of a matrix. We'll pick a matrix A, which is M cross N over R. I'll take R just for simplicity, or C also there are similar statements which are true. Let's say it represents a linear map T from Rn to Rm with respect to standard basis. Notice I'm saying standard basis is very important. If you change the basis here, all that I say will not be true. Okay, very important to keep in mind. Okay. So T star now I know is a linear map from Rm to Rn and it's represented by the conjugate transpose A or A transpose over line bar. I can put a notation like that. But since entries of A are real, you can say the conjugation is irrelevant. So it's simply A transpose. Once you have that, you can go back and look at how these spaces are related, and you'll see the very natural thing that's happening with respect to the matrix, right? Range of T star is the column space of A transpose, and that's nothing but the row space of A, and clearly that is the null of A perpendicular. right, the dual of the, I mean, the orthogonal complement of the null of A. Okay. Now, null of T star is the null of A transpose, that is left null of A, and that is the column space of A whole complement. Okay. So, the same things, the same thing we had on range of T and null of T star and all those connections clearly plays out and gives you a very nice grasp if you look at it in terms of 4 fundamental subspaces of the matrix. Okay. It is A and A transpose, rows become column. If you look at null, the null will be a complement for the row space, left null will be a complement for the column space, that is it. Okay. And what about this relationship that dimension of range of T should be equal to dimension of range T star? That is nothing but row rank equals column rank, right. Range of T star is nothing but the row space, range of T is the column space, both of them have the same dimension, row rank equals column rank, and that gets reformulated as dimension of range T equals dimension of range T star. Okay. So, I think maybe that point I have not written down, maybe it is worth writing down. Dimension of range T star equals dimension of range T is exactly equivalent to dimension of column space. Okay, maybe I should write row space first. Row space of A equals dimension of column space of A, which is nothing but row rank equals column rank. Okay, the familiar result that we proved using another trick in the previous one of the previous lectures. You can see when you define adjoint in a very clear fashion. Okay, so this sort of gives you a feel for what adjoint is, its connections with the matrices we've been talking about. Notice this important thing is the orthonormal basis. This adjoint thing works very well only when you work with orthonormal basis. If you change basis, you have to do something more to find the adjoint. It's not very obvious or easy. Okay, so keep that in mind. Okay, so now let's move on and study slightly more advanced notions with adjoint. Like I said, the adjoint plays a very important role, and to do all that, we'll need to look at what happens when two operators are composed, in particular what happens to the null spaces. We've been looking at it in some exercises and applications. I've been talking about if you have a product AB, what is null of AB in as a function, I mean what is the connection between null of AB and null of B, null of A, etc., etc. So let's formalize that first, and that will play a key role when we study more advanced things with adjoint also. Okay. So let's say we are back to linear maps now. You have a linear map T from V to W and another linear map S from W to U. Now ST is a composition of the two maps, and it will take you from V to W, right. That is also a linear map, we know that. Now the crucial thing we want to study is how is the null space of ST connected to the null space of S and null space of T. That is what I want to do. Okay. So here is the crucial result. I think I've alluded to this in earlier discussions, but let me just formally write it down. Let's define a new subspace. This is a subspace of W. Okay. Remember, ST takes you from V to U, but it goes through W, right? And in that W in the middle, I'm going to define a subspace. What is this subspace? It's the range of T, which clearly is a subspace of W, intersect with null of S. Okay. The range of T is a subspace of W, null of S is again a subspace of W. Okay. So clearly their intersection will again be a subspace. So that subspace I am calling as NW. Okay. So some NW. Okay. This subspace is very important. This will play a crucial role in how to determine null of ST. Okay. So in particular, here is the relationship. Okay. The dimension of null of ST equals dimension of null of T plus dimension of this NW. Okay. So this is the important relationship. Okay. And sort of makes sense in so many different ways. I'll draw a picture soon enough to clarify this, but let's go through and try and prove this first in some fashion, and we'll understand. So maybe I should draw a picture right away before we, or maybe I should wait for the proof to come out and then I'll draw it. Okay. So the first step in the proof is to figure out how this NW enters the picture, right. So, you will see how this NW enters the picture here. Supposing I give you a vector V which is in the null space of ST, okay, what do I know? STV equals 0, right, and that is if and only if TV is in null of S, okay. So, this is a crucial relationship here. TV has to be, so STV equals 0 means TV, right, after you did TV has to be in the null of S, right, only then STV equal to 0. This is all basic definition. Now, remember TV is in the null of S, but TV clearly is also in range of T, right. TV by definition is in range of T, it also has to be in null of S. So, if V is such that V is in null of ST, then TV must be in range of T obviously, but it should also be in null of S. So, what does that mean? TV is in the intersection of these two, so TV has to be in NW, okay. So, this is how this NW enters the picture and it plays a very important role, okay. So, I will draw a picture soon, but let us just bring up the rest of the proof and then I will draw the picture. So, from this argument we clearly see that null of ST is the set of all V such that TV belongs to NW, okay. So, this is crucial, there is nothing else in the null of ST, right. If V is in null of ST, this is all if and only if and only if and only if, it all works out like this. Is that okay? So, think about it, null of ST is the set of all V such that TV belongs to NW. From this it comes out, okay. So, we will start thinking of basis for null of ST. See, for looking at dimension we need to look at basis. I think at this point maybe I should draw the picture, it will be helpful I think. So, this picture has 3 subspaces, there is V and then there is W. I will draw it a bit bigger so that a lot of action happens in W, and then you have U, isn't it. So, V is the first vector space, this T operates from V to U, and then you have S operating from W to U, V to W, T operates from V to W and S operates from W to U. You have these 2 subspaces here, interesting ones. There is this range of T and let us say there is this null of S, okay. And then you have this nice little intersection here, which maybe I will draw in some green, this is NW, okay. You will also have other interesting subspaces, right. You will have null of T will be here, okay. And you know how this operator works, right. So, under T what is going to happen? The whole V will go to T and null will go to just one point here, right. So, the 0 will be somewhere here and this whole null will go to that point, okay. So, keep that in mind, okay. Hopefully, you can see that. And then what happens when I go from W to U? Remember, once I do ST, I start with a V here, I will only come to range of T, whatever is outside of range of T is irrelevant to me, and this S when it operates I can restrict it to range of T, right, and then this range of T will take me to something here, okay. This will be a subset of range of S, okay, which is where you will go, and this guy will take me to the 0, isn't it. This NW will take me to 0 when I restrict it to this, okay. So, when I want to look at null of ST, I am looking at the subspace of V which takes me to NW, right, subspace of V which takes me to NW. So, what will that be? So, now if you look at any other point here, some other point here, what will that come from? That will come from a translate of null of T, right. So, there will be a translate here, okay. So, maybe I can draw it like this, okay. So that will take you to this any other point, isn't it? So there will be similar translates, I am just drawing it grossly out of proportion, but you can still see for every point here there will be a translate here, isn't it? So all of these guys will take you to this subspace NW in W, and I have to just characterize that. What is this subspace here? What is this null of ST, which is a set of all V such that TV takes you to NW. So how do I do this? This is not very hard if you visualize this a little bit. I am not going to be too detailed on this, I will just provide the final answer in some sense, okay. So first thing you will have is a basis for null T, okay. Everything in null T will definitely take you inside the NW, it will take you to 0, there is no problem. What about other things? For that, let me look at this very closely. I will come up with a basis for NW, okay. I will call it W1 to WR, okay. R could be the dimension of, okay, I have said R here, it is not R, sorry, it is NW, sorry about that, okay. So this is the basis, and I will try to find solutions in V for this equation TV equals Wi, okay. So what is that solution? It is Vk plus I, just one solution, let us say, okay. So you take a Vk plus I such that Tvk plus I equals Wi. This is true for 1 to R. Now how do I know that a solution definitely exists? How do I know that a Vk plus 1 will definitely be there? It's you know, Wi actually belongs to the range of T, okay. So definitely there should be at least one Vk plus I. So you take your favorite Vk plus I, it does not matter what it is, you take that. So you collect all these vectors in V, just one vector in V, which will take me to the basis vector of NW, okay. Now my claim, here is the claim, okay, so maybe I should do this here also, this is NW. This is the claim, the basis for null of ST is simply the original, the basis for null T, V1 to Vk, and then these new Vk plus I that I have, Vk plus 1 to Vk plus R, that is the basis for null T, okay. This needs a little bit of proving, and I am not going to prove that for you in detail in this lecture. I will let you think about it, but it is sort of intuitive. From the picture I drew in the previous slide, you can sort of figure out why this should be true. You take a basis vector for basis for NW, figure out solutions for the equation TV equals the basis vector, and add it to the null vectors, null basis, you should get the basis for null of ST, okay. So I will leave out some technical aspects of the proof to you. If you are interested, you can fill it out, otherwise also it is okay. But the most important result is this, okay, this NW is naturally entering the picture in W, and the dimension of null of ST is dimension of null of T plus dimension of NW, and the basis is formed in this fashion. And from here you can see, you know, dimension of null of T comes in and dimension of NW comes in after that, okay. So that picture is very important. You have V here and you have this NW here, and 0 in U, right, comes only through this NW, right. So and then that is the connection. And how do you get to NW? You can either come from the null space, or you can come from other parts of V which will take you inside NW. And how do you solve for the set of all V that takes you to NW? You can take a basis for NW, find individual solutions and put them together, you will get a basis for the subspace that you are interested in, okay. So that part needs a little bit of proving. I will let you do the proving yourself, okay. So this picture is very important, and this will play a key role in several of our proofs later on, and it is also good to know that what happens when you compose two linear maps. How do you think of the null space? It gives you a lot of interesting ideas, okay. So there is a special case of this which is very important, okay. When you compose two operators, as before, there is an operator from V to W, as an operator from W to U, you compose it ST, you get an operator, you get a linear map from V to U. I keep saying operator, operator, operator. So it's again, it's compositions of linear maps, it's not really operator, okay. So you may want to replace this with linear maps, okay. So you keep saying this operator all the time, but you know, keep a flexible definition in your mind. When I say operator, it could be a linear map also, okay. So that's okay. So anyway, what is this special case? This is the special case, okay. So a very special situation is when range of T and null of S do not intersect, okay. So in the previous picture we saw that range of T and null of S intersected in a big way. The special case is when they intersect only at 0, okay. So they are sort of disjoint mostly except for that 0, okay. In that case, null of ST equals null of T. Okay, so there is nothing else, right? NW is only 0. The only way you go to 0 in U through S is through that 0 in W. There is nothing else in W which can take you to 0 in U. So you better be in the null space at T. Okay, so that happens when that intersection is 0. So it's sort of like, S and T are sort of nicely related to each other, as in S does not diminish T in any way. T takes you from V to W, and S does not further diminish the dimensions by operation. Okay, so for instance, a simple thing to think of is, suppose S is an invertible operator, right? U and W are the same. If S is an invertible operator, clearly ST and T will have the same null space, right? It's invertible. But you don't need S to be an invertible operator. S could be a linear map, but its null space could intersect trivially with the range of T. In that case also, you have the same effect of the invertible operator like thing, except that it's only specific for this particular T, right. So if you pick your T and S carefully to match or not sort of mismatch in the range and null, you can almost have that invertibility effect with ST. Okay, so that's the idea here. And once you have null of ST being null of T, you can also see that range of ST equals range of T. It's almost as if this property is very important. So when S is restricted to the range of T, it's 1 to 1. So it doesn't do any further damage to the transformation. Okay, it doesn't reduce dimension in any other way. Okay, so this special case is very, very important, and this special case applies for us when it comes to adjoint. Okay, so you'll see why that is interesting. Okay, so these two operators especially are very crucial in a lot of linear algebra studies. Okay, so you have a linear map T, you have its adjoint T star. Okay, now I can define an operator, and I'm right, this is an operator this time. I can define two very, very interesting operators, two compositions, T star and T star T. Okay, these are two different compositions clearly, right, because V and W are not the same. T star is an operator from W to W, okay, and T star T is an operator from V to W, okay, I'm sorry, V to V, okay. T star is an operator from W to W, and T star T is an operator from V to V. These two operators are very different even in terms of what they do, but they are very nicely connected and they have some very nice properties. In fact, the previous properties that we saw of how operators compose, right, how one operator does not destroy the other operator's thing, these two operators are like that. They really have those nice properties of composing properly to give you what you want. Okay, so that plays an important role later on. So let's see each of these things correctly. So T star T is an operator from V to V, and now I know null of T star is actually range of T orthogonal complement, right. So T and T star are like that. So clearly when this is true, we know that null of T star and range of T intersect only at 0. Okay, so our good composition result is true, right. So it's almost like the invertibility composition. So null of T star T is null of T, and dimension of range of T becomes equal to dimension of range of T star T, and we also know it's equal to dimension of range of T star. So this T star and T star T, they are all very closely related. So many of their properties, and they will all look very similar in some sense, right. So this is the high level feel for why that is true. Okay, so this is the reason. Same thing with T star. T star takes you from W to W. It's an operator, and I mean, so where are we heading here? See, when you look at just the linear map T V to W, one of the problems in studying that was we couldn't repeatedly apply T, right. So when we could repeatedly apply something with operators, we got this wonderful eigenvalues, and that shed a lot of light on what that operator was. Now this T star trick will give you that repeated application possibility. Okay, so you have T, you apply composite with T star, right, T star T, you get an operator now, and this operator looks sort of similar to T, right. It's close to T in some sense, in a loose way. It sort of represents T. It doesn't take anything away from what T is doing. So, and now T star is an operator. T star T is an operator. You can start thinking of eigenvalues for it, you start thinking of invariant subspaces for it, and all sorts of interesting things you can study. Okay, so this is a nice thing. So again, for T star, the same thing is true. Null of T is range of T star perpendicular. So these two intersect only at 0. So you have all these nice relationships that are true. And you can see also even here, right, so these two are also equal. I didn't call it out, these two are all equal. Okay, so T star, T, they are all equal in dimension. Okay, so hopefully this gave you more clear idea of adjoint and its use when studying linear maps and its connections to linear operators, etc. Okay, so in the next lecture or so, we will start looking at operators and their adjoints. So far we have been looking at linear maps and adjoints and how adjoints play a role in understanding linear maps and all that. Now we will start looking at adjoints of operators in the next lecture and look at eigenvalues and nice properties from that point of view. Thank you very much.